Okay, so good afternoon to all. Let's start the session. So we already performed the three experiment. The first one is verification of the truth table of the logic gates. The second one is the universal gate, which is NAND gate and NOR gate. So the NAND gate and NOR gate work as a universal gate. And in the last lab, we performed the experiment number 3, which is the adder circuit. So which is used to add the two binary numbers. Suppose we have two numbers A and B, and we have to add these two numbers. Then we require the adder circuit. So generally for adder again, the adder is having two different circuit or two different types of adder which we have, a half adder and full adder. So half adder is used to add two binary numbers or two bits, and the full adder is used to add three numbers. Okay, so today we have to perform the experiment number 4. Okay, so experiment number 4, which is to study and verify the half subtractor and a full subtractor. Okay, as we have a half adder and full adder, which is known as a adder circuit, same way we have a subtractor circuit. So what is the application of the subtractor circuit? The subtractor circuit is used to subtract the two binary numbers. Subtractor circuit is used to subtract the two binary numbers. So again, as we have a half header and a full header. So the what is the application of half header? Half header is used to add the two binary numbers, while as the full header is used to add the three binary numbers. Same as the subtractor circuit, the half subtractor is used to subtract. Half subtractor is used to subtract the two binary numbers, while as the full subtractor is used to subtract the three binary numbers. So this is the today's experiment we have to perform and study about the half subtractor and the full subtractor circuit. Okay, so what is the half subtractor? Actually, half subtractor is used to subtract the one bit from the other and produce the difference. So we have a subtractor, as we all know, because we already complete the binary subtraction. So in binary subtraction, if we subtract the two numbers, then we have output a difference. And suppose if you want to subtract, if you want to subtract 1 from a 0, then we require the borrow. Okay, so the output, the half subtractor having a two input, suppose A and B. We have a A and B and we have to subtract B from A. So A minus B. Then there is a two possibilities of the output. One is known as the difference and another is known as the borrow. Another is known as a borrow. Okay. Again, the subtractor having a two different circuit known as a half subtractor and a full subtractor. Now, what is the half subtractor? Half subtractor is used to subtract the two binary numbers. So this is the block diagram you can see of the half subtractor. Suppose we have a two input A and B, and we have to subtract B from A, so A minus B. So there are two possibilities. There are two possibilities of the output. One is known as the difference and another is known as a borrow. So let's make a truth table of the half subtractor. You can see here. Now I want to subtract A minus B. So 0 minus 0. As we all know, the 0 minus 0, so my difference is also 0 and my borrow is also 0. So 0 minus 0 is 0. Then 0 minus 1. So 0 minus 1 is not possible. So what we have to take? We have to take borrow from the next bit. We have to take a borrow from the next bit. So that 0 becomes 1 0. So 0 minus 1, my difference is also 1 with a borrow 1. My difference is also 1 with a borrow 1. 1 minus 0, difference 1, borrow 0. 1 minus 1, difference 0, borrow 0. So now you can see the truth table. So for you can check the difference. So what is the truth table of difference? 0 0 0, 0 1 0, 1 sorry 0 1 1, 1 0 1 and 1 1 0. 0 0 0, 0 1 1, 1 0 1 and 1 1 0. So which gate having a truth table like this? Which gate having a truth table like this? For 0 1 it is 1 and for 1 0 it is 1. And for 0 0 and 1 1 it is 0. Which gate having a truth table of this? Can anyone tell me? Very good, Keval Mohit. It's a very good answer. It's exclusive OR gate. Okay, so for difference, we are using the exclusive OR gate. Okay. Okay, so difference is indicated by simply exclusive OR gate. Now a borrow. So for we can check the truth table of borrow. So the truth table of borrow is for 0 0 it is 0, for 0 1 it is 1, for 1 0 also it is 0, for 1 1 also it is 0. For 0 1 it is only 1. Okay, for 0 1 only it is 1. So we do not have directly a gate which having a truth table like this. Okay, which having a truth table like this means truth table of this means 0 0 0. For 0 1 only it is 1. For 1 0 also it is 0 and for 1 1 also it is 0. So how we can make the equation of a borrow? Okay, so when the output of borrow is 1, we have to check its input condition. When the output of the borrow is 1, we have to check its input condition. So when the borrow is 1, when the input A is equal to 0, A is equal to 0 and B is equal to 1. A is equal to 0 and B is equal to 1. And as we all know, 0 means a dash or you can say bar and 1 means as it is. So the equation of borrow is A bar B. Equation of borrow is A bar B. So let's draw the logic diagram. So for difference, we are using the exclusive OR gate. Okay, for difference, we are using the exclusive OR gate because the difference is denoted by the exclusive OR gate. So this is the difference of exclusive OR gate. And for borrow, we have the equation A bar B. So I am taking the input A, giving to the NOT gate. So what it gives A bar, and taking the B and giving to the AND gate. So finally, it gives the output A bar B. Finally, it gives the output A bar B. Okay, so this is the logic diagram of a half subtractor. This is the logic diagram of the half subtractor. Also, we'll see the theory of the half subtractor. So let's move for the theory. Now you can say, what is subtractor circuit? So subtractor circuit take the two binary numbers as the input. So we have a two binary number as the input and two binary number as the output. Okay, so for half subtractor we have two input and two output, same as in a adder, but adder do the adding of the two numbers while the subtractor is used to subtract the two numbers. Okay, so the two outputs of the subtractor is a difference and a borrow, So there are two types of subtractor, half subtractor and a full subtractor. Again, what is half subtractor? So half subtractor is a combinational circuit. So see, these all are the combinational circuit. Adder circuit, subtractor circuit are the combinational circuit, which is used to perform the subtraction of a 2-bit. Suppose we have a two input x and y, then we have to subtract y from the x, so x minus y, and we have two output known as a D and B. So for D it is difference and B it is borrow. So this is the block diagram of a half subtractor. You can see this is the truth table of the half subtractor. 0 minus 0, difference and borrow both are 0. 0 minus 1, both are 1. 1 minus 0, difference 1, borrow 0, and 1 minus 1, again both are 0. And this is the logic diagram. So anyone having any doubt in a half subtractor? Otherwise we will move forward for the full subtractor. If anyone having any doubt in a half subtractor, you can unmute yourself and ask me a question, or you can ask me a question in a chat session. And if it is clear, please write down a clear in a chat session. So I will move forward for the full subtractor. Okay, so thank you, Mohit. Now the full subtractor. As we have a full adder which having a three input A, B, and C in. What is C in? It is carry in. It is carry in. So same as in a full subtractor, which having a combinational circuit, which is used to subtract three binary numbers. So you can say 3 bits. So again, A and B is the same. Now third one is the borrow in, or you can say B in. and again the full subtractor having again the two outputs. So subtractor circuit having a two outputs only, either it is a half subtractor or it is a full subtractor. Subtractor circuit having a two outputs. One is the difference and another is the borrow. So you can see this is the block diagram of the full subtractor. So we have a three input A, B, and the third input known as the borrow in. Third input known as the borrow in, and we have a two output known as the difference, and a borrow out. B out means borrow out. So again, so this is the full subtractor. So let's verify the truth table. So as you can see here, 0 minus 0 minus 0. So 0 minus 0 minus 0 is difference also 0, borrow also 0. Then 0 minus 0 minus 1. So 0 minus 0 is 0 and 0 minus 1. So 0 minus 1, difference also 1, borrow also 1. Next one, 0 minus 1 minus 0. So 0 minus 1, again 0 minus 1. So difference is also 1, borrow is also 1. Now 0 minus 1. So 0 minus 1, difference 1, borrow 1. But again, with a difference again minus 1. So 1 minus 1. So again, so finally we have difference 0, borrow 1. Difference 0, borrow 1. So 0 minus 1 minus 1, difference 0, borrow 1. Next is 1 minus 0 minus 0. So 1 minus 0 minus 0 is difference 1, borrow 0. Then 1 minus 0 minus 1. So 1 minus 0, 1. 1 minus 1, 0. So difference 0, borrow also 0. Then 1 minus 1. So 1 minus 1 is 0. Minus 0. Again 0. So difference 0, borrow 1. Now again 1 minus 1 minus 1. So 1 minus 1, here it is 0. And 0 minus 1, difference 1, borrow 1. So this is the truth table of the full adder. So generally full adder is made by the two half subtractor, same as the full adder. Okay, same as the full adder is made by the two half adder. So subtractor is used to subtract. Full subtractor is made by the two half subtractors. The first half subtractor is used to subtract the first two number, which is x and y, and the difference of that we are giving to the second half subtractor. And in second half subtractor, the second input is third input is b in. So same as in a full adder is made by the two half adder, the full subtractor is made by the two half subtractor. Full subtractor is made by the two half subtractor. You can see in the your screen. So HS1 means half subtractor 1, HS2 means half subtractor 2. So we have a two borrow output. So both the borrow from the half subtractor 1 and the half subtractor 2, we are adding together, and finally we have a B out. So here we have to use the OR gate for the borrow. So we have a two borrow, one from the half subtractor 1 and another from the half subtractor 2, and we are adding that two borrow, and finally we have a final borrow which is known as the B out. Final borrow which is known as the B out. So this is the another block diagram of the full subtractor. And this is the logic diagram. This is the logic diagram of the full subtractor. Okay, the logic diagram. How the logic diagram will make? See, Okay, so this is our half subtractor number 1, and this is our half subtractor number 2. Okay, and both the half subtractor here, see here the half output of the half subtractor B of the first half subtractor. This is also borrow from the second half subtractor. Suppose you can say this is the half subtractor borrow of the first half subtractor B1. This is the borrow of the second half subtractor B2, and we are adding this borrow of the both the half subtractor, and finally we have a B out. So the B out is equal to borrow 1 plus borrow 2. What is borrow 1? Borrow 1 is the output borrow of the first half subtractor, and B2 is the borrow of the second half subtractor. So we have to add these two borrows, and finally we have a B out. Finally we have a B out. So this is the so this is the final logic diagram of the full subtractor. This is the final logic diagram of the full subtractor. Let's also show the theory which is available in the virtual lab. You can see same circuit. Let me copy paste this. Copy, and I am pasting to the same circuit. Okay, same circuit I am copy pasting here. So you can see this is the first half subtractor, and this is the second half subtractor, and the borrow of the both the gate adding by using a OR gate, and finally we have a borrow out. Okay. So anyone having any doubt in a full subtractor? Anyone having any doubt in a full subtractor? Otherwise, I will move forward for the pre-test. Okay, so I think no one have any doubt. So let's move for the pre-test. Now it's your time. You have to give the answer. So this is the first question. Half subtractor is used to perform the subtraction of 2-bit, 3-bit, 4-bit or 5-bit. So A, B, C or D. Give me the answer in a chat session. half subtractor. Half subtractor is used to perform the subtraction of how many bits? 2 bit, 3 bit, 4 bit, or 5 bit. Okay, Mohit and Bhavisa Brunda gives the answer. X, the half subtractor is used to subtract the 2 bit. The next one, for subtracting 1 from a 0. For subtracting 1 from a 0. So what we have to do? 0 minus 1. We used to take blank from neighboring bits. So what we have to take from the neighboring bit when we are taking subtracting 0 from a 1. Okay, Mohit, Bhavisa and Man also gives directly gives the answer. The option is okay. Vrunda also gives the answer, so no need to read the option. So we have to take a borrow from the next bit. How many outputs are required? Sorry, how many output are required for the implementation of a subtractor? 1, 2, 3, or 4. So how many output we have? How many outputs we have in a subtractor? Either it is 1, or it is 2, or it is 3, or it is 4. So A, B, C, D. How many outputs we have in a subtractor circuit? See how many are? Give me the answer. See, in subtractor we have a two output. One is a difference and another is a borrow. So answer is 2. The next one, let the input of the subtractor is A and B. So we have two input A and B. Then what will be the output if A is equal to B? So if A is equal to B and you have to subtract A minus B, then what is your output? 0, 1, A, B. Again, I am repeating the question. Suppose I have two inputs of the subtractor, which is A and B, and I have to subtract that two numbers A and B. So I have to do A minus B. So what will be the output when A is equal to B? Okay, Mohit gives the answer, Amit gives the answer, Keval gives the answer. Very good. Because A equal to B, so A minus B, if both are same, A and B both are, suppose you can say 2, 2. So 2 minus 2, 0. Suppose both are 10. So 10 minus 10, 0. So if A equal to B and we have to subtract it, then the answer will be 0. The last question. Let A and B is the input of the subtractor again. Okay. Then the output will be, so which gate we are using for the output of the difference? Either A exclusive or B, A and B, A or B, A exclusive nor B. So which gate we are using for the difference? Difference is denoted by which gate? C. Only for in chat only you are giving the answer. You can check and give me the answer. Which answer is right? A exclusive or B? A and B? A or B? A exclusive nor B? Okay. Amit gives the answer. Keval gives the answer. Okay. Vrunda also gives the answer. Very good. So we are using the exclusive OR gate for the difference. Now submit the quiz. Check. Okay. So we have all the 5 are correct. So this is the pre-test. Let's move for the. We do not need to read the theory. Directly go for the simulation. So there are two simulations available. One for the half subtractor and another for the full subtractor. So I will also share the link with you. See, today we will perform the two experiment, okay? Because in another batch is the six experiment is completed, and today this is only our fourth. So today we will perform the two experiment. The first is this half subtractor and full subtractor. Another is also easy. Okay. Then also we will end the session early. So you can click on the link and do the simulation by yourself also. Uh, Let me show you the simulation of a half subtractor. So just same, we have a LED. You can see. Let me zoom it out. We have a two LEDs here. The LED number one is for the difference. Once it is red means difference is 1, and if it is not glow, what that means, difference is 0. And another LED is for the borrow. So first we require the supply. So switch on the supply. So 0 minus 0. So 0 minus 0 is 0 minus 0. So both are 0. You can see difference also 0 and borrow also 0. So both the LED will off, is off. Now 0 minus 1. 0 minus 1 means difference is also 1, borrow is also 1. Okay, so you can see both the LEDs on now. So add to the table. Now 1 minus 0, you can see difference only 1, borrow is 0. Again add to the table, and 1 minus 1, again both are 0. So see, this is very easy simulation. Each and every time you just switch on and switch off. Let me show the simulator 2 also. So this is the simulator 2. If you click here on circuit, the circuit will be shown. Now we have to put the value, take 0 0. So my difference is also 0, my borrow is also 0. Click on check. If it is correct, then in remarks it will write the correct. You can see here. Then 0 minus 1, my difference is also 1 and my borrow is also 1. Click on check. If it is correct, it's written correct. Then 1 minus 0, difference 1, but my borrow is 0. And the last one is 1 minus 1. So for 1 minus 1, again both are 0. So this is the simulation of the half subtractor. Uh, Now you can also do the simulation by yourself and do the simulation of half subtractor and full subtractor. Okay, so anyone having any doubt for the simulation, how it will work? Let me show you the simulation of the full subtractor also. So click on the full subtractor. Again, in full subtractor, we require the numbers of IC, but the process remains same. We have two outputs. You can see like here in your screen, difference and the borrow, which is shown by the LED. Now, instead of two input, we have three inputs. So first we have to switch on the supply, which is a 5-volt supply required for the each and every IC. So without supply, IC cannot work. So we are giving the supply to the IC. Now all are the zero. So all are the zero. The difference and borrow is also zero. Now add to the table. Now 0 minus 1. You can see difference and borrow both are 1. 0 minus 0 1 0. So for 0 1 0 again both are 1. For 0 1 1 my difference is 0, my borrow is 1. Now next one is the 1 0 0. So 1 0 0, difference is 1, borrow is 0. 1 0 1, both are 0 0. 1 1 0, again both are 0 0. And lastly 1 1 1, so both are 1. So this is the truth table starting from 1 to 8. You can see this is the truth table. Okay. So same truth table you can simulate by yourself in a simulator 2 also. In simulator 2, you have to write the input here and you have to write the output here, and then you have to click on check, and then there is a remarks. If your answer is right, then remark shows you correct, and if your answer is wrong, then your remark shows incorrect. Let me show you let me take a 0 0 1, and I am taking here 1 0. I know it's incorrect, so I am clicking on check. You can see the remark shows the incorrect. Okay, so when you are writing the correct truth table, then and then it will shows you the correct, and then it will shows you the correct. Otherwise, it will show you the incorrect. So anyone having any doubt in a simulators? Otherwise, we will move forward for the post test. Anyone having any doubt? If it's no doubt, please write down a clear. So we will move forward for the post test. Okay, thank you, Mohit. Keval. Now again, it's your time. You have to give the answer. The first question is, okay, Mohit already gives the answer. The full subtractor is used to perform the subtraction of how many bits? 2, 3, 4, 5. Mohit gives the answer. What about others? Full subtractor is used to perform. Okay, Keval also gives the answer. So let me click on the answer, which is 3 bits. So full subtractor we have is used to subtract 3 bits. You can say A, B, and B in. So third bit is borrow in. Suppose the output of a subtractor is given by, again when we are asking for the output, it's only for the difference. So suppose if we have a three input A, B and X, then what is the output of the, or what is the equation of the difference? A and B exclusive or X, A X or B X or X, A or B nor X, A nor B X or X. Keval gives the answer, Mohit gives the answer. A X or B X or X. The output of a full subtractor, the output of the full subtractor is same as the output of the full subtractor is same as the half header, a full header, a half subtractor, decoder. Again, we are working when we are talk about the output. We are talking about the difference only. So the output of the full subtractor is same as the half header or the full header or the half subtractor or the decoder. A, B, C or D. Okay, Keval use the answers. What about others? See, either you are right or wrong, just give the answer. Only Keval, Mohit, and sometimes Runda and Amit gives the answer. What about others? Either you are wrong or right. See, it doesn't affect your grades right now. Okay, so you just have to try. Okay, there are lots of students available here. Hers, Aditi, Aves, Dharmajit C, Dusty, Keval. Name is just, you can also try. It's okay. It's you are not sure. It's okay. But actually, the final answer is B, full header. Because what is the output equation of the full header? It's also the full header for some. It is also indicated by the exclusive OR gate. If I have here, let me show you the full header. And okay, so you can see here, this is the circuit of full header. Okay, so again A and B we are giving to the XOR gate. So A XOR B and C in, again we are giving to the XOR gate. So final output is A XOR B XOR C in. So A XOR B XOR C, same as the subtractor. Suppose we have three input A, B, C, then the equation of the difference is A XOR B XOR C. So the final output is same as the full subtractor, full header. Sorry. The next question. Sorry. What does the minuend and the subtrahend denotes in a subtractor? their corresponding bits of input, its outputs, its inputs, or borrow bits. Okay. So what does the minuend and supplyend denotes in a subtractor? It denotes, okay, Mohit gives the answer C. So suppose now the last question is for the half subtractor. Let A and B only two inputs. So this is that's why it is half subtractor. Let A and B is the input of the subtractor. Then the borrow will be given by which equation? A and B dash, A dash and B, A or B, A and B. Okay, so most of you are giving the answer A dash and B. Now submit the quiz. So our all the question is right. Our all the question is right. And finally, if anyone having any doubt on this, there are some references. So if you click on the references, there are the books, and also there are the links and the videos how the full subtractor and the half subtractor is made on the a breadboard. Uh, as today, due to this COVID, we have to perform the experiment in the virtual lab. Otherwise, if we all are in the college, we have to perform the experiment. We have to perform the experiment in a breadboard only. So we have to take the ICs and the resistors, supply, and the ICs. Okay, you can see here the ICs is there. So that's how we are performing the experiment. Suppose if we are in college, that's how we are performing the experiment. Okay, by ourselves. So anyone having any doubt in this experiment, half subtractor and full subtractor? Anyone having any doubt? Otherwise, we will move forward for the next experiment. Okay, next experiment theory we already studied. Now the next experiment is actually this is our experiment number 5, but in a virtual lab it is the experiment number 11. So the next experiment is the conversion of binary to gray and gray to binary. Binary to gray conversion and gray to binary conversion. If everyone is remembered, this is the part of unit number 1 which we already covered. So we have a gray code, and we can convert a gray code into a binary number and binary code into a gray number by using a exclusive OR gate. By using a exclusive OR gate. So here also, from the conversion of binary to gray and gray to binary, we are using the exclusive OR gate. And what is the output of the exclusive OR gate, or you can say the truth table of exclusive OR gate? For 0 0 it is 0, for 0 1 it is 1, for 1 0 also it is 1, and for 1 1 it is 0. So for 0 0 0 and for 1 1 it is 0. So this is our next experiment to verify a binary to gray and gray to binary conversion using a NAND gates only. So here they are working on the NAND gates only. Otherwise, actually binary to gray and gray to binary conversion are made by the exclusive OR gate. So this is the aim. Go to the theory directly. So generally binary number is the default way to store a number because our CPUs and the systems are work on the binary numbers only. But there are some applications of the gray code also. There are some application of the gray code also. So, and there are some a property of the gray code which is very useful. So what is the property of gray code? That the two successive numbers differs in only one bit. Differs in only one bit. Let me show you how it will be differ in only one bit. Uh, okay, so suppose we have two binary numbers, let's say A and B, and when we are writing the table, we are writing like 0 0, then 0 1, then 1 0, and lastly 1 1. So you can see from 0 0 to 0 1, only one bit will change. B 0 to 1. A remains same, but from 0 1 to 1 0, 0 1 to 1 0, both the numbers is changed. A is converted from 0 to 1 and B is converted from 1 to 0. Because this is a binary number, but suppose it is same number, if you want to write in a gray code, then what the gray code is have 0 0 is same, then 0 1 is also same because it will differ from only one bit, and from 1 0, instead of 1 0, the next number is 1 1 and the last number is 1 0. Now you can check any successive numbers, only one bit will change. From 0 0 to 0 1, only B will change, A remains same. From 0 1 to 1 1, only A will change from 0 to 1, B remains same. And from 1 1 to 1 0, only B will change, A remains same. So this is the property of gray code. Okay, what is the property of gray code? The two successive numbers differ by only one bit. Two successive numbers differ by only one bit. And this is the application of gray code. This is the application of gray code. So what is the application of gray code? Gray code is used in a KMFC in theory Now K-map is starting. So in K-map, we are using gray code only. Also in error correction code, we are using the gray code. Or the communication also, we are using the gray code. What is the meaning of communication? Okay. So mostly the gray code is used to communication between machine and the system. Suppose if you have a motor, and if you want to measure the speed, then in the shaft of the motor, you are putting the speed sensor, and that speed sensor works on the gray code. So we have to convert a binary to gray and also gray to binary. So first B to G conversion. So this is the two rules is used to conversion of binary to gray, or you can say gray to binary. Okay. So the first rule is, as we already covered in the theory session, all of you aware about that. Then also let me finish the theory. So the first bit MSB remains the same. Okay, the most significant bit of the gray code is always equal to the MSB of the given binary code. I will give you the example also. And other bits of the output of gray code can be obtained. How can we obtain the other gray code? So we can get the other gray code by XORing the binary code bit at the index and its previous index, at that index and the previous index. Okay, so let me show you. I will take you the example. Suppose I have a binary number 01. This is my binary number. Okay, and I have to convert that binary number into gray. So what the first rule says, the MSB of the binary remains same when you are converting into gray. So MSB, which is the most significant bit, or which having a highest weightage or highest value, which remains same. Now what we are doing, we have to XOR this number. XORing that number, that index with the previous index. What is the rule says? XORing binary code bit at that index with the previous index. So at that index with the previous index. So 1 XOR 1, or you can say 1 plus 1, it is 0. Then this one with this 0, so 1 plus 0, you can say 1 plus 0, 1. And 0 plus 1, so it is 1. So that's how we are converting binary into gray. We have to add that index with the previous index. So XOR gate, we have to focus on XOR gate. So what is the XOR gate output? For 0, 0 it is 0, and for 1, 1 it is 0. But for 0, 1 it is 1, and for 1, 0 it is 1. Okay. So here we are focused on the 4 variable codes. So for 4 variable codes for conversion of binary to gray, suppose you have 4 binary bit, and if you want to convert that 4 binary bit into gray, then in gray code also you have a 4 bit. So for 2 binary number you have 2 gray code, 2 bit gray code. For 3 binary you have 3 gray code, and for 4 bits you have 4 inputs and 4 outputs. 4 inputs and 4 outputs. So this is the equation of the binary to gray conversion. Your MSB or most significant bit is remains same for the gray. So B3 is equal to G3. Then for G2 you have to use the that index means B2 and add with the previous index means B3. So B2 XOR B3 is equal to G2. B1 XOR B2 is equal to G1 and B0 XOR B1 is equal to G0, and this is the logic diagram. This is the logic diagram of the binary to gray conversion. Binary to gray conversion. Let me show you how it will work. Now is it visible? So you see the first MSB will remain same. So B3 is directly come to the G3. This B3 is directly come to the G3. Now for G2 we have to add B2 and B3. For B1 again B1 and B2, and for G0 B0 with a B1. Now you can easily understand it in this figure. B3 is directly to G3, then B3 and B2 it will come to the G2, B2 and B1 it's for G1, and B1 and B0 it is for G0. So this is the conversion of binary to gray. This is the conversion of binary to gray, and for 4-bit conversion of binary to gray we required 3 exclusive OR gate. We required 3 exclusive OR gate. Suppose if you have a 7 binary bit, and if you want to convert into a 7 gray bit, then you require 6. Then you require 6 exclusive OR gate. So how many bits you have? You required, suppose n bit, for n number of bit you required n minus 1. You required n minus 1. Yes, Keval, very good. N minus 1 exclusive OR gate. So this is for the binary to gray conversion. Anyone having any doubt up to this binary to gray conversion? And let me show you the truth table also. So this is the truth table of binary to gray conversion. You can do it by yourself also. 0 0 0. It's all are same. So again binary to gray is also 0, because the 0 first remains 0, 0 with 0, 0 with 0, and 0 with 0 is 0 only. Then the 0 0 1, it's also same, 0 0 1. From the second one it will be changed. From 0 0 1 0 it is 0 0 1 1. For 0 0 1 1 it is 0 0 1 0 up to last. For 1 1 1 1 it is 1 0 0 0. So this is the binary to gray code converter truth table. Okay. Anyone having any doubt in binary to gray conversion? And if it's no doubt, please write down the, it's clear. Okay, thank you. The next one is the gray to binary conversion. So again, it is same. The first rule is same. Either it is gray to binary conversion or it is binary to gray conversion. The MSB remains same for G to B and for B to G. For G to B and from B to G. Now other, how we can do the others? Let me take an example so you can easily understand. Suppose I have a number, you can say 1, 0, 0 and 0. Suppose this is my gray code. Okay. Now we have to convert gray into a binary. So again, the first rule is same. The MSB remains same. Now for the next binary number, we cannot add a that number, that index with previous index, but what we have to do, we have to add answer, or you can say B3 with a G2, next bit. So 1 plus 0, 1, again 1 plus 0, 1, and again 1 plus 0, 1. So what we have, the equation, you can say B3 is equal to G3. But what is the equation for B2? Now B2 is equal to B3 with a G2. What is the B1? B1 equal to B2 XORing with a G1. And what is the equation of B0? B1 XOR with the G0. So this is the equation of gray to binary conversion. This is the equation of gray to binary conversion. So other bits of the binary code, how we can obtain? So we can obtain it by checking the gray code bit at that index. If current gray code bit is 0, then copy and previous binary code bit, else copy invert the, do not focus on that rule. Okay. Focus on this equation which I already written. So again, for 4-bit a gray number, we have a 4-bit output. And these are the another method of writing the equation. and this is the figure. See, G3 is equal to B3. Now B3 with a G2, it gives B2. B2 with a G1, it gives B1. And B1 with a G0, it gives the B0. So this is the figure of gray to binary conversion. This is the figure of gray to binary conversion. And finally, we have a truth table of gray to binary conversion. Now, anyone having any doubt in gray to binary conversion? Okay, so let's move for the pre-test. Okay, so the first question is a code converter like a binary to gray and gray to binary. So code converter is a logic circuit that inverts the given input, converts into decimal number, converts data of one type into another type, converts to octal. Okay, Mohit directly gives the answer. Keval also gives the answer. So code converter is the, okay, Amit also gives the answer. A code converter is the circuit which is used to convert a data of one type into other type. Now, the next question, what is the primary use of the gray code? Coded representation of shaft's mechanical position, turning on off software switches to represent the correct ASCII code indicating the angular position of a shaft on a rotating machinery, to convert the angular position of a shaft on a rotating machinery into hexadecimal. Okay, Amit gives the answer. Sorry, Mohit gives the answer. Man gives the answer. Yes, Mohit, you are right. It is the coded representation of the shaft mechanical position. See how we can understand A is right. It is not used to on-off switches. It is not convert the ASCII code, not converts into ASCII code and not converts into hexadecimal code. It is a gray code. It's a different code. So the correct answer is A. Yes, Vrunda also right. So the next one is 4-bit gray code can be converted into 1-bit binary, 2-bit binary, 3-bit binary, 4-bit binary. So Mohit gives the answer, Keval gives the answer. Okay, Amit also gives the answer. It is 4. One also gives the answer. As we have 4-bit gray, then if we convert into a binary, then it is 4-bit binary. Vrunda also gives the answer. Okay, very good. So gray to binary conversion can be implemented with which gate? AND, exclusive or NAND, NOR. Which gate we are using for the gray to binary or binary to gray conversion? Same gate we are using. Okay, Mohit and Vrunda gives the answer. Keval gives the answer. It's B. We are using the exclusive OR gate. Okay, so last one. A binary code that progress is such that only one bit changes between two successive codes. Which code it is? 9's complement, 8421, XS3 or gray code. Okay, so Mohit, Keval and Vrunda gives the answer that it is gray code. Amit also gives the answer. Very good. Submit the quiz. You can check all the 5 out of 5 of your answer is correct. Of your answer is correct. So now let's move for the. Do not focus on the procedure again. Focus on the simulation. So move for the simulation. So let me share a link with all of you. So you can do the simulation by yourself also. Let me show you the simulation. Sorry. Okay, so there are two options: binary to gray code converter, gray to binary code converter. Click on any one. Okay, so I am clicking on binary to gray converter. So see, this is the circuit. So this is our binary numbers. Switch off means 0 and switch on means 1. So again we require the IC to supply. So this is the supply. Click on, double click on that. So it will return like that, connected. So you can see all are 0. For 0 0 0 0, output is also 0 0 0 0. For 0 0 0 1, you can see here for binary red means 1 and for gray green means 1. For 0 0 0 1, output is 0 0 0 1. Now 0 0 1 0, output is 0 0 1 1. For 0 0 1 1, 0 0 1 0, let me show you for 1 0 0 0 0, all are 1. For 1 0 0 0, output is 1 1 0 0. For all are 1, 1 1 1 1, output is 1 0 0 0. So this is a simple conversion. You can make a conversion by yourself also. Okay, so do the simulation of binary to gray and gray to binary by yourself. I will give you the 5 minutes for that. So anyone having any doubt on this, how we have to do the simulation? Just you have to write down the truth table and you have to check either it is correct or not. And also you can take a printout of this and put in the manual. See, you have a circuit with the truth table. Just I am giving the 6. You can take the truth table of all the 16 from 0000 up to 1111. Okay. And same way you can do the conversion of gray to binary, and it is the same circuit. Now click on the supply. Suppose my output is there are some error. Let me solve. Suppose my input is 1000, so output is 11111. Just add into the table. So you have to add this into table up to 16, starting from 000 to 1111. So anyone having any doubt in this simulation or in this experiment, gray to binary or binary to gray conversion? If you do not have any doubt in simulation, then we will move forward for the post test. Yes, see, we do not have a more time. That's why I'm not asking anyone to share their screen. From the next lab, I will ask anyone to share her or him screen. Okay, you do the simulation by yourself also. So now move for the post test. So this is the first question. Convert the binary number into gray code. So you have to convert this binary number into gray. Okay, Mohit gives the answer and Keval gives the answer. What about others? We have to convert this binary number into gray. So the first MSB remains same. The next, the first to the next bit. So 1 plus 0 it is 1. Then 0 plus 0 it is 0. Then 0 plus 1 it is 1. Then 1 plus 0 it is again 1. And for 0 plus 1 it is again 1. So no, Keval, you are right only. The first answer C is correct. Okay, so next question. If a two system have a different codes, then a circuit inserted between them is combinational, sequential, combinational sequence or conversion circuit. Which circuit we have to use? if we have a two system which work on the different codes, you can see my machine sensor will work on a gray code and my computer system work on a binary code. So which system we can use in between? Combinational circuit, a sequential circuit, combinational sequence circuit, or conversion circuit. So, okay, Vrunda, Mohit, Keval, Amit gives the answer. It is conversion circuit which can convert one code into another code. The next question. The reflected binary code. The reflected binary code is also known as the BCD code, gray code, ASCII code, and binary code. Okay, so Vrunda gives the answer, Mohit gives the answer, Keval and Amit also gives the answer. It is B code, B or gray code. So reflected binary code is also known as the gray code. Now, code is the symbolic representation of discrete information, continuous information, decimal information into binary, or binary information into decimal. What is code actually? So code is the symbolic representation of discrete information, continuous information, decimal information into binary, and binary information into decimal. So Mohit gives the answer. What about others? If you are correct, then also please give the answer. Okay, Keval gives the answer. He is not sure about that. What about others? Vrunda gives the answer. See, C and D is wrong because code is not the thing which convert decimal into binary and binary into decimal. So we have two options only. Either it will be A or it will be B. So generally, the code and the binary numbers are the, you can say, it is not the continuous thing. It is not the continuous thing. So it is the discrete information. Okay. The next question is convert gray code. So we have to convert this gray code into binary. So my gray code is 0101. Okay, so Mohit, Man, and Brunda gives the answer. Keval also gives the answer. So it is B. My MSB remains same, so it is 0. So A and C is already wrong answer because its MSB is 1. So we have to select from B and D. Then we have to check the 0 with the next one is 1. So 0 plus 1 is 1. Again answer is 1. So answer with the next bit. So 1 plus 0 is 1. Again answer with the next bit. So 1 plus 1 it is 0. So B is correct. Now click on submit the quiz. So our all 5 out of 5 question is right. All the 5 out of 5 question is right. So this is about the post test, and if you want to learn more about the gray to binary and binary to gray conversion, so there are lots of references available. So you can read the books. Also, there are the links from which you can easily learn more about the code converter, which is binary to gray and gray to binary. So uh, So now, anyone having any doubt about this two experiment, so you can ask me a question by unmute yourself, or you can ask me a question in a chat session. Otherwise, it's over from my side. If you have a doubt, you can ask me a question. And if it's clear, please write down a clear. Then we will, I will take the attendance, and we will end this session. Okay. So thank you everyone for attending this lab session. Today we perform the two experiment. The first one is about the subtractor, so half subtractor and full subtractor, and the second one is the code conversion. So in particular, code conversion, we are focused on the binary to gray and gray to binary conversion. So thank you everyone. So now you can write down your enrollment number for the attendance, and those who write down their number, if they want to leave, they can leave the session. Okay, so 93, 87, 111, 132, 92, 88, 110, 99, 105, 140, 94, and 87, 133, 143. Okay, so those who have already written their number, if they want to leave, they can leave the session. So thank you everyone. Now I am closing the meeting.